Good evening, everyone. My name is David Mytton. I'm the founder of Arcjet. So I'm going to talk to you this evening about what we're doing in Arcjet, which is a security as code product. It allows you to implement functionality into your application like bot detection, rate limiting, personal information detection, but it's all as code inside your application. I'm going to tell you about a little bit what that means by looking through the code and how we're actually doing it. But one of the enablers of how we're able to do Arcjet today is WebAssembly. And when we're thinking about security and what we're doing with our product, we have a couple of goals. So we want to try and analyze every request that comes into an application. And we want to do that locally in your environment. We can do it on your laptop. So in development, you can write your security rules and you can test them locally. You can then run it in staging and run it in production, and it's the exact same code. And we do that to avoid latency, and if you're processing personal information, the worst thing to do with that is to send to the cloud somewhere. And so we want to keep it all in your environment. And then when we're analyzing arbitrary HTTP requests coming in, we really want to keep those in a sandbox. We want to minimize the opportunity for any arbitrary code to execute, and to maintain security guarantees, a sandbox is the perfect environment for that. And we also want native performance because we're analyzing large requests potentially, we're applying multiple rules, and we want to do that as fast as possible so that we can return and allow or deny response and then not slow down your application. Now, these three characteristics sound very suspiciously like what WebAssembly can provide. And so that's why we chose it as a technology. So if you deploy a web application to production today, then a typical architecture looks something like this. The client connects right at the top there, and the request comes in. And a typical way to protect that is to put some kind of network firewall in front of it, probably Cloudflare, maybe Fastly or Akamai or AWS's WAF product. And those products are great for analyzing traffic as it comes into your application on the network. It's the perfect place to do anti-DDoS protection, where you have large volumes of malicious traffic that you just don't want to see in your application at all. Though they apply rules, you generally have no idea how they perform. You don't know how fast they are, you don't know what they're doing to your traffic. But they'll come to a conclusion based on their own analysis and the rules that you configure, and they'll either block the traffic so you never see it, or it goes to your application. Well, really, first it goes to your server, whichever server you're running, maybe a Node server, maybe Nginx, maybe Caddy, in a load balancer somewhere, and then it hits your application. Now, your application has no idea why a request has been sent to it. It doesn't know what rules were processed in the security context, so it doesn't know why it decided to allow that request through. And equally, if the request is denied, your application just doesn't see it. And so the way that Arcjet works is to completely remove the need for the majority of that network processing. Every cloud platform today provides DDoS protection out of the box as standard, for no extra cost. And you'll often see the likes of Vercel and AWS talking about the largest ever DDoS attack that they have ever detected, and they transparently mitigated it for all of their customers. You don't need to do anything. Now, the way Arcjet works is it's an SDK. You install it as a dependency into your application. It's npm install Arcjet or whatever package manager you're using. And then you can call it as part of your application request flow. So it means it can sit in the middleware if you want to just have a very quick implementation and intercept every single request. Or you can put it in particular route handlers and have it execute with the context of that request. And the idea is that Arcjet will intercept every single request, apply the rules that you define, and then it will give you a response back in your code. And you can either decide to accept our recommendation, allow or deny, but you get to inspect all of the decision reasoning behind that. So you can create custom logic. So you could re-authenticate a user, or you could apply dynamic rules because you know they're signed in and they're on a particular pricing plan. You get all of this analysis, and the idea is it enriches every request context with the security metadata of that request. I'm going to take you through the flow of the code. What you as a user of Arcjet will see is currently our JavaScript SDK. And so we just bring it in just like a normal JavaScript library, and then we're instantiating our client. And this is where the WebAssembly component starts up. And you define your rules in code. So here I have a bot detection rule. I'm going to allow all search engines to access this page, but you can choose what you want to do there. And actually, this is going to be a sign-up form, and so we're also going to do a validation process, and we're going to validate an email address. And so this is perhaps on a post handler. Now, in a real application, you would instantiate this client outside of the request handler so that it starts up once. And then for every single request, you'll call aj.protect. This is just a simplified example. And the idea is that you pass through the request, we analyze it, and then we give you a response back. Here it's just, is it denied? And then you can take a custom decision, but you get, I've kind of cut off all the rest of the code, but you get access to everything that goes on behind the scenes. So then what's actually happening here? Well, we're defining our access to the WebAssembly through a WIT definition. And this allows us to create bindings between JavaScript and WebAssembly, because they're two completely different environments, and they're not compatible with each other directly. And so we have to define an interface between them. This is the first part of a WIT file, and we're just defining a simple interface. Here we're defining a few different things that we want to pass in into the WebAssembly as part of the configuration. So you can determine things like, what do we consider a free email address? Gmail is free, Yahoo is free, Apple.com is not free. You might want to distinguish between those depending on what your business goals are. Disposable email addresses might indicate fraud or someone trying to spam whatever it is you're protecting. And then we also want to validate whether the email address has MX records, because that might indicate whether it can actually receive email. And then if you may remember Gravatar as a service from a long time ago, allows you to get a little avatar associated with your email address. That's an indicator that it's a real person who's gone to the effort of setting up a Gravatar account. It's something you can detect against as part of the rules. And then this is the second part of the WIT file. I just cut it into two so that you can see the text really big on the screen. And the key thing here is that we're exporting a function, which is what's called in the JavaScript. So the request comes in, you call aj.protect. Our JavaScript SDK intercepts the HTTP request, pushes it into the WebAssembly module, and it's pushing it through a few different functions that we expose. One of them is the bot detection. It's a bit too complicated to show on a large screen, so I picked the email address as a simpler example. But one of those functions is valid email. And this is a perfect thing to do in WebAssembly because it's a parsing function. We want to pass the email address string and make sure it is a valid email address according to the RFC. And then there are a couple of configuration options that you can pass through if you want to change what we consider to be a valid email. And then all of the logic in Arcjet is actually implemented in Rust and is compiled into WebAssembly. And so what this WIT definition is doing is allowing us to define a boundary between JavaScript and Rust, and it's executed inside WebAssembly. All of the core functionality is just pure Rust, but we have to translate between Rust and JavaScript. And so we provide this boundary, which is kind of a mixture of the two. And so this is valid email function is what is exposed to the JavaScript and is what is defined in the WIT file. So when we compile the WebAssembly, the bindings generate the JavaScript functions that we can call in our SDK. But behind the scenes, it's calling Rust. And now this is where the request enters into the Rust functions. And then we do a little bit of conversion because there are types that are not available in JavaScript that are available in Rust and vice versa. And when we're working in Rust, we want to work in Rust native types. And so we do a bit of conversion here. And then all this function is actually doing is calling the real Rust, which is behind the scenes. And so what this allows us to do is to write the majority of our security functionality once in Rust. And then we create language-specific bindings so that when we generate the WebAssembly, we can have an interface between that particular language, JavaScript in this case, into the WebAssembly that's calling Rust behind the scenes. There's more to this, but this is just a standard Rust function that is then doing the email validation and will return a result back to the client. And then it goes all the way back up the stack and does the conversion back into JavaScript, takes the Rust types and makes them available in JavaScript for us to return to you as the user of the SDK. We also do this in Go. Now, local first is a goal for the SDK, but it's not always possible to do 100% of the time. So for instance, you can't make network calls from WebAssembly, or at least not easily, and not in a way that is easily translatable across multiple environments. And one of the things we do is to look at the IP address of a request. We have a large database of IP addresses and their reputation. And so we enhance the decision of every request with a call to our API. Also, in some cases, WebAssembly is not available. The environment might be very constrained. And so the SDK might just say, can't run WebAssembly here. We'll just let the API do everything. But we don't want to rewrite everything in Go, because we've already written it in Rust. And so we just call the exact same WebAssembly from Go. And we do that whole process again. We have our own bindings that we generate, which translate the Go types into Rust-compatible types, and access it through the boundary that is the WebAssembly module. So this is the exact same function, but it's calling in Go. And that means that when you use our SDK, the ideal situation for most environments is processing inside WebAssembly. It's very fast. But in the cases where WebAssembly is not available, or we want to do a fallback to the API for some reason, then we can still execute the exact same code and give you the exact same result. In some cases, you can have language-specific differences between, particularly hashing functions can be implemented in different ways across different languages. But by having it all implemented in a single language, executed using WebAssembly, means we can guarantee the result's always going to be the same. So to build all this is a fairly standard build process. We just compile it to the WebAssembly target within Rust. But then we do some optimization, and we use Wyzer to pre-initialize or pre-compile the WebAssembly. Because, for example, if you're running your application in a serverless environment, you don't want to have to compile a WebAssembly module on every single request. So we pre-compile it for you using Wyzer, and then we snapshot it and take the pre-initialized version and bundle that in the SDK. So when we're instantiating it in our JavaScript SDK, it's instantiated, pre-compiled, ready to go. And then we also use wasm opt to optimize the output. And this runs through a few different stages because we have to trade off the file size of the WebAssembly component with the speed. Now, we want to instantiate it as fast as possible so that we can respond to every request. But we also have to load the module. And the larger the file size, the slower the load time. And so we have this trade-off depending on the environment. Serverless environment where you're perhaps loading it constantly for every single request, or perhaps every so often, depending on whether it's a hot function or a cold start. But if you have a long-running server, it's just a standard node server, you're only doing it once on startup, then you can trade off the slightly slower instantiation time for a larger binary. The JavaScript ecosystem for running WebAssembly is the most mature, and there's a lot of really good open source tool chains that allow you to do a lot of this out of the box. So we use Jco, which is what generates the JavaScript bindings from our WIT definition. So it takes that WIT definition, converts it into JavaScript, and then we call that from our SDK. You can do something very similar in Python using wasm time. You can generate the bindings, but other language support is not as mature. And so we've written our own tool called Gravity to do this for Go. It's in the process of being cleaned up so we can open source it, but it allows you to do the same thing, takes the WIT file and generates bindings for Go so you can call the same WebAssembly modules. I've written a lot more detail about this on the blog, so if you have any questions or want to read exactly how we're doing it, then visit blog.arcjet.com. And our SDK is open source, so you can go in and have a look at the generated WebAssembly and see what we're actually doing. I'm happy to answer any questions by email and afterwards as well. Thanks a lot.